go through the review a little bit. I'm going to ask you guys the questions. I'll ask you guys to solve the questions in 1, 2, 3, 4, 5, 6, 7. Everyone's here now? In groups of 3. Okay, so I get you guys to go into groups of 3 and try to solve these problems as a group. So let's get started. So we talked about electrical potential. Can you guys see this properly? Do you mind, Michelle and William, could you close the eyes behind you? Amanda, could you do that one on the Now that I've sucked the light out of the room, we're in the right mode. I don't know how to. It comes out as automatic. Is that better? It might come back on. If you remember, we're talking about electrical potential and electrical potential energy, and that's what we're talking about today. We figured out how to draw equipotential lines, and then we know that the equipotential lines are what? How do you interpret the equipotential lines in relation to electric field? You guys remember that? It's part of your lab. And an awkward class, guys. You have equipotential lines, and you have electric field lines. What is their relationship? Yep. They are perpendicular to each other. Thank you. All right. And we know that there is electric potential, equipotential lines everywhere, not just in a place where there are a huge concentration of currents. Here in this room, there's going to be a huge amount. In this country, there's going to be a huge amount. There's electrical activity. There's going to be anywhere, even in nature. We know that electric field is a vector. We know that equipotential lines are not vectors, so that's why there are arrows for the electric field and no arrows for the equipotential lines. Everywhere on the equipotential line, or maybe you should answer me this: what does it mean to be equipotential? What does equipotential mean? Martin?
Well, that means the force that you can get out of it is the same. Well, the energy you can get out of it is the same along that line. The energy of the electric field has the same force, has the same power anywhere on that line.
Exactly, right? Like the way we are saying it, but that's right. Anywhere along any given line, the amount of energy that some random charge might have is going to be equal, all right? So we talked about this. Just as electric field depends on space and allows us to compute force on any charge. So it's the potential energy on the generic charge. So energy per charge, or joules per coulomb, if you remember the unit. And electric potential depends on space and all that. It is not a vector, and electric field is a vector. We talked about the relationship between work and voltage and all that stuff. So remember, it's the energy divided by the charge that's going to give you that potential, the changing potential. We also we derived this equation for it. Remember that the units for potential energy is always joules, energy is always joules, and potential is in volts. Both are scalar quantities. There is no direction to energy, there is no direction to voltage, and that. So we're going to do this one together, and I'm going to ask you guys to do the rest on your own. And here is a very simple example of how to calculate, or when to calculate, potential and potential energy. So find the electric potential at the dark point. I think you can write it down. Kind of bound to this table. So if I were to do this one here, and I'm looking for the potential of that red point at the top, right? And at that point, what is the charge of this point here? The trick question. What is the charge of that point there? Rowan? There is no charge, right? So when we're looking at potential, we're not looking at anything with a charge. We're looking at just like a location, all right? what did we talk about just in the previous slide? What was the formula for potential? Do you guys remember? Close? Not Q over R, but missing one letter. Yeah, potential is KQ over R. So voltage is equal to KQ over R. And so we could easily find out what the potential is based on these two charges, because those are the Q's that I'm talking about. Yeah, Bronwyn? Yeah, so this location, if we measure its potential, it's the theoretical energy that a charge might have if it were given the certain, right? So if you remember, PE is equal to KQ1, Q2 over R. And if we divide it both sides by Q, this Q and this Q cancel out, and I'm left with KQ over R, which is potential. Okay? All right, so we have this relationship, and we could easily calculate potential at that point. Does it matter that one is at an angle, if there's an angle here, that there's a distance here? Does all that matter? No, because it's a scalar quantity. Sorry, I'm going to bump into you a bit. It's a scalar quantity, which means that you kind of disregard all that stuff, and you just add up the voltages to give you the total voltage. So the total voltage is going to be the voltage from this charge and the voltage from this charge added together. So let's do that. So we have K times 2 nanocoulombs, positive 2 nanocoulombs, over R, which is 5 centimeters, plus, and then we add the charge, the potential from the other charge, which is negative K times 1.0 nanocoulombs over 0.04 meters. Okay. Yeah, you're going to have to convert this into regular coulombs. This is going to be 10 times, 2 times 10 to the negative 9 coulombs. And this is going to be 1 times 10 to the negative 9 coulombs. And remember that K is 9 times 10 to the 9. Who can do this in their head, actually? Yeah. Because I just realized these nanocoulombs and the this nanocoulomb and this thing are going to cancel each other out. And dividing by 0.05 is the same as multiplying by 20. So it's 18 times 20? 360? So this is 360 minus, and then this is 1 times 9 divided by 25. Times 25, right? Because dividing by 0.04 is the same thing as multiplying by 25. There's 360 minus 225, is that it? And that's going to be equal to, this is the hardest part, 100 and what? 135 volts. Cool, we did that in our head. All right, so The answer would be 135 volts. Any questions about that? That's the last one I'm going to do before I send you off to the next one. So I want you guys to get into groups of 3. Try to answer these questions. They're kind of like, some of them are challenges, some of them are math problems. But I want everyone in the group to try and figure out the solutions, all right? Because some of them are a little bit trial and error and understanding the difference. One thing, if I were to go back to this problem, right, and ask you, okay, here we calculated the potential. It's very easy. We just calculated 2 potentials and we added them together. If I were to ask you the electric field at this point, then you would know that, well, hold on, electric field, that's a vector, and positive charge is an electric field going towards it or away from it? Away, and this one goes towards it or away from it? All right, towards, so that means that if I were to do electric field, let's say I was thinking about it, this one here, the positive charge, is going to give me an electric field in that direction, and this negative charge is going to give me an electric field in this direction, so the resulting electric field is going to be in that direction. You guys remember doing that? Okay, so that's the kind of things that you're going to need to do in today's practice problems in your groups. Okay, so get together in groups of 3, please. Do this one, this one, this one, this one, and this one. So practice 1, 2, 3, 4. All right, when you're done one, show me the answer because I want to see how you guys got to the answers. Go. Groups of 3. There's 18 of you, so there should be no one left out. Marco, join a group. William, join a group. Give me actual concrete examples where you put more charges in space. I want actual examples. Try to determine where things go. That's when the vectors are canceled each other out, right? Yeah. Okay. So think of it that way. The electric fields, the vectors of the electric fields have to cancel each other out. Why? There is already how much funding? How much funding? Does someone think that I can answer the first one? At least one of these examples? You got one example? Okay. Make that make more. Okay. That's not an assumption, that's fine. That's great. Let's go on to another example. Okay, but I mean like. Try to do like two dimensional, instead of one dimensional. So having it in a line, maybe where. You got it? Charges. So where you're measuring, where are you measuring the electric field? In the middle. Okay, and what is the electric field? Zero. Sure.
No, for driving it means that there's this has to be like right, whole positive charge will create.
Your false positive will cancel each other out. We have an opposite. Actually, double what it would be.
Yes, so like now there's an edge.
Okay, so the potential here is zero, not zero, that would be one. That's what it's asking.
Yeah.
Right off the bat. You got a chart.
Yeah.
You have, and if you add or subtract that, it will find that's the point where potential, the electric field is zero, potential.
So we could actually make that.
Yeah.
And I was just I click and then load it.
No, 22% is how much of it was quote unquote found from other sources. Is there a way to download the document? Click on the document.
big deal, because like,
No, 22 is not, because everyone's gonna write work percentage to measure
okay.
for, in electricity and magnetism, NYV, everyone's gonna write.
All right.
So there's always gonna be a certain level of,
Okay, so, for the electric,
do
yeah,
no, and you should all wear those now.
okay.
Right? Go ahead and see if there's any market